For this next example, we are given a graph, and what's essential is that we read carefully, right? This is the graph of the derivative. It's not the graph of the original function. Okay, so we're going to figure out information about the original function just based on the graph of the derivative. Okay, so in order to do that, since this is the derivative, that means that we can read off the critical values of the original function. So I'll put those in red, not because they're critical values of this graph, but because those three red dots, that's where the first derivative is 0. So those will be the critical values of the original function f of x. And let me label the points here. That's going to be that little peak, and then this is going to be C, and that's going to be D, and that's going to be E. That'll be useful just to have names for these points. So just based on looking at the graph of the derivative, we can see that the critical values of the function itself happen at A, C, and E. Those are the three x values where the first derivative is 0. Okay, now what do these other 2 points represent? Those are going to be inflection points. Because if you think about it, what's the tangent line look like here? The tangent line is horizontal, but that's the tangent line to the first derivative, right? So that means that the second derivative will be 0 at b and d. F prime prime will be 0 at b and d. These are going to give us inflection points in the original graph. That'll be spots where the concavity changes. So using all this information, let's try to sketch the original graph, and I'll put it right below so that we can try to line up the A, B, C, D, and E, okay? I'll do my best. Alright, so to the left of A, the derivative is negative. That means that the function itself is decreasing. And now the function itself, there's a little bit of ambiguity. If you think about it, if we had some f of x whose derivative was this, but then we added, say, 3 to f of x, the derivative of 3 is 0. So we can kind of shift f of x up and down. You'll see what I mean. I'm just going to draw a version that works. So here we have some local minimum corresponding to that critical value, because now the first derivative is positive. The first derivative is positive when the function is increasing. So the function starts increasing, there's an inflection point at b, and then it has this little local maximum right there at c. That's this. Sorry, my scale isn't quite correct, but that corresponds to this c. And then we die back down, we have an inflection point at d. And then what happens at e? Here, the first derivative is negative. That means we're decreasing, right? We've been decreasing all the way since c. But we're going to keep decreasing after e. So this critical value is one of those critical values where you just flatten out, but then continue to decrease. So that's a sketch of the graph of f based on just the graph of the derivative. Let me first point out the critical values, the spots where the derivative is 0. That was at A, C, and E. Those are spots where the tangent line to the original graph will be flat. We have a local minimum there. Using the first derivative test, the first derivative is going from negative to positive, so that had to be a local minimum. We'll have a local maximum there. First derivative went from positive to negative there. But here at this critical value, we're not going to have either a local max or a local min. That's actually an inflection point too. So B and D are going to be inflection points, but there's actually another one here at E, right? It's changing from concave up to concave down. So these are inflection points of the function, and we've determined by our analysis that there is another inflection point at E. So 3 inflection points, B, D, and E. Let me write that down, or just rather notate my color coding. These purple circles always correspond to inflection points. That's spots where the concavity changes. Okay, very nice. Okay, in this problem, it's kind of similar to the last one in that we're given a graph which is not the original function, but this time we're given just the second derivative. So this is the second derivative of the function that we're interested in, and we're going to sketch the graphs of the first derivative, f prime, and the original function, assuming that they both go through the origin. There's some ambiguity because of this issue with constants, so we could choose lots of graphs that would work, and we're just going to assume that both f prime and f go through the origin. That's going to make it easier to sketch. Okay, in order to do this, I've included these 3 points, x1, x2, and x3. And now we need to start thinking about what this means here on the second derivative. So at x1 and x3, the second derivative is 0. So ultimately, those will be inflection points on the original graph. But before we get to that, let's just think of the second derivative as the derivative of the first derivative. If the second derivative is 0 here, those are like critical values for the first derivative. Those will be spots where the tangent line to the graph we're trying to draw is flat. And now we know that we're supposed to go through the origin, right? So let's just start moving to the right from the origin and think about what this information means. It means that we're increasing. This graph is going to be increasing because this is the derivative of this graph. So we're increasing, and then we have a little local maximum here at x3, and then we'll die back down like that. What happens to the right? I didn't quite get the curvature correct. That's okay. It's just a sketch. Well, it's going to be something like this. We're going to have a local minimum at x1, and then we start increasing. So this change from decreasing to increasing to decreasing corresponds to negative, positive, negative. And as we'll see, that's going to correspond also to the change in concavity in the original function f of x. Again, this is the derivative. We just went from the second derivative and figured out what the first derivative must look like. Well, let's see, I better put in my x1, x2, and x3 just to keep track of everything. Okay, so that looks good. Now let's see, what's the next thing to do? That's the graph of the derivative. We now want to graph the original function. So now we'll use that anywhere that the first derivative crosses the x-axis must be a critical value for the original function. Okay. And let's also note, before we do that, that in between these two critical values, the first derivative is negative, right? Because here we're below the x-axis, those are negative values. Here the first derivative is positive. Here the first derivative is positive. And here the first derivative is negative. That's also going to help us out because these different possibilities, those correspond to whether the function itself is increasing, decreasing, increasing, or decreasing. So now I'm going to sketch the graph of the original function. Maybe I'll put it next to them so that we can kind of see them all in one spot. I was going to do it vertically, but I think I would rather just have enough room here to see it all. Okay, here we go. We said that in the function we said that we should assume that both f prime and f go through the origin. So here this is going to be f of x, and I'm going to start at the origin. what's happening? As we move from the origin, the first derivative is positive, and so the function itself is increasing as we move away from the origin. We reach a local maximum at this critical value, and then we turn back around. So that's what's going to happen to the original function. You can see that there's an inflection point here. That's that point x3. So that's going to be a change from concave up to concave down in the original function. That corresponds to the second derivative changing signs, right? Notice that the second derivative is positive in this range of values. F prime prime is bigger than 0. It's negative over here, and it's negative to the left of x1. That corresponds to the original function being concave down, concave up, and concave down. So we'll see that in this sketch that I'm making. x3 is that inflection point, that change from concave up to concave down. Okay, what about to the left here? Well, let's see. Here we have a critical value of the original function, and to the left, f prime is negative, so the original function is decreasing. Oh, so that means that we should have been decreasing down to this local minimum. And now there's one other critical value there out past x1, and that'll be another local maximum, like this. So that's a sketch of the original function. We have x1 right there. That's again an inflection point, changing from concave down to concave up. Notice that we're concave up in between x1 and x3, just like I was saying here. And we're concave down to the left of x1 and to the right of x3. And then x2, we don't really see it reflected on the graph. It has to do with this kind of funny curvature. It's not the best sketch, but you know, good enough for government work. Let's complete the graph by just filling in those critical values that we found in the previous steps. And we'll also characterize them as local maxima or local minima. Those two critical values, those are going to be your local maxes. And then the one at the origin, that's going to be your local min. Okay, very nice. Now let's see, finally, let's just characterize among the points x1, x2, and x3, where each of these functions is largest and smallest. Okay, you might see some problems like this on the homework. So notice that f prime, the second derivative, is largest, I don't mean overall, but just among those three x values that I've singled out. It's largest at x2 because it takes this max value right there, and then it's smallest because it's 0 at both x1 and x3. Alright, what about for the first derivative? Let's scoot on down here and look at the first derivative. Notice that the first derivative, among just the 3 points, x1, x2, x3, right, just among these 3 points, it's biggest here and it's smallest here. So it's largest at x3 and it's smallest at x1. Okay, what about for the original function? Oh, I should have labeled x2. It's right there. Where is it largest and smallest? Well, it's going to be smallest at x2 because that's so close to this local min. And is it largest at x1 or x3? It kind of depends on the curvature. I didn't do a very good job graphing it, but I meant this origin to be pretty close to x1, actually. So I think I drew this a little bit too high. Based on the symmetry here, this should have been shooting up faster. So if I had drawn a better picture, we would have seen that the function is largest, the function itself is largest at x3 and is smallest at x2.